question, three grammars are given and we have to find which of them is LL1 grammar. For the grammar to be in LL1, it should be free from left recursion. And if we see grammar G3, here left recursion is there. So grammar G3 will not be LL1. And if we construct LL1 parsing table for grammar G1, will not be getting any multiple entries. So G1 is LL1 grammar. And if we construct the parsing table for grammar G2, then we'll be getting multiple entries under for the row A, under the column B. The multiple entries would be A gives epsilon and A gives BAB. That means B predicts both A gives epsilon and A gives BAB. So whenever there are multiple entries in the parsing table, the grammar is not LL1. So here G2 is not LL1. So here the only grammar which is LL1 is grammar G1. So here the correct option is option B.
Here there is a common data question. The data given is, consider the following arithmetic expression: S is equal to x plus y into w minus z. Assume that the number of clock cycles required for the execution of instructions in any of the CPU organization is as follows. Add and subtraction instruction takes 1 clock cycle each. A multiplication instruction takes 2 clock cycles each for execution. All other type of instructions takes 1 clock cycle each. Question number 1 on this data is, how many clock cycles are required to evaluate the given arithmetic expression using single accumulator CPU organization? Here in single accumulator CPU organization, we are going to perform all the operations in only AC register. Whatever the operands that are there in the expression, first of all we used to take them into accumulate register and then operations will be performed. So here the given expression is S is equal to x plus y star w minus z. So first we have to load the x value into AC register. For that we use the instruction LDA. LDA is a content of AC will be loaded with a memory word. LDA X. LDA X means AC receives the data from memory at address X. So M of X gives to AC. Again directly we can add Y, because X plus Y we have to evaluate. Add Y indicates AC receives AC plus, already AC has got the X value, plus M of Y. M of Y is content of memory at address Y. Now X plus Y value is there in the AC register. We have to perform W minus Z. For performing W minus Z, we have to vacate the AC. Let us say the AC will be stored in some temporary location of memory by using STA instruction. STA T, where T is the temporary location. So M of T receives the AC value now. Now M of T contains content of memory at address T is the AC value, that is X plus Y. Now freshly W value will be loaded into AC. LDA W. So now AC receives the content of memory at address W. Again we have to subtract Z from this, that is SUB Z. So AC receives AC minus M of Z, content of memory at address Z. Again we got AC value as W minus Z and the memory content at address T will be X plus Y. These two should be multiplied. We can make use of MUL instruction. MULT. So now AC receives content of AC, that is X plus Y star and then M of T. Content of AC is W minus Z and M of T will be X plus Y. These two will be multiplied. Result is now available in AC. This must be stored in a variable at S. So that means we can say that is STA. Store content of AC at S. Content of memory at address S. That means M of S receives the value from AC. So finally, so this requires 1 clock cycle, because all other instructions require 1 clock cycle. Addition 1 clock cycle, STA 1 clock cycle, LDA 1 clock, SUB 1 clock, MUL 2 clock cycles, and STA 1 clock cycle. 1, 2, 3, 4, 5, 6, 8. Total 8 clock cycles are required for this. So option B is the right option. How many clock cycles are required to evaluate the given arithmetic expression using general register CPU organization with 2 address instruction? So this is the second question on the common data given. Here we need to find out the number of clock cycles required to evaluate the arithmetic expression using general register organization with 2 address instructions, because general register organization can be having different types of instruction formats. We can have 2 address instruction formats, we can have 3 address instruction formats. So it is mentioned clearly that we have to use the 2 address instructions. So the expression given is S is equal to X plus Y minus W minus star W minus Z. So this is the expression given. So the set of instructions for this will be, first of all, we have to take the value of X into some register, because all operations will be done in general registers here. Let it be R1, move R1 comma X. So R1 receives the data from memory at address X. So X value will be taken into R1. Again directly we can add Y for the R1, that is R1 comma Y value. So these are the 2 addresses. One is the register address, the other is the memory address here. So now add R1 comma Y indicates R1 receives content of R1 plus content of memory at address Y. That means X plus Y is there in R1 now. Now we evaluate W minus Z with other register by using move instruction, data transfer instruction. Move some R2 comma W. So R2 receives the value of memory at address W. Now next we have to subtract Z from this, that is SUB R2 comma Z. SUB R2 comma Z. That means R2 receives R2 minus M of Z, content of memory at address Z. Now R2 contains W minus Z, R1 contains X plus Y. These two must be multiplied. So we can make use of MUL instruction for multiplication. We can put both the register operands. As much as possible we try to use register operands, but initially some value must be there in register that is to be taken from memory. That is why we have to use one memory address initially. MUL R1 comma R2. So R1 receives R1 star R2. Again this result is available in R1. We have to save this result in a memory at addresses, so that we can use move S comma some R1. So M of S receives the data from register R1. So for this one clock cycle, for this 1, 1, 1, for multiplication 2, for this 1. So total 7 clock cycles are required for execution of this. So option A is the right option for this. Total 7 clock cycles are required for evaluating this arithmetic expression using general register CPU organization with 2 address instructions.